earlier we learned about the normal equations and how they can be used to find an orthogonal projection onto a span. That is, you're trying to best approximate a vector that does not fall in your span. Well, these can be used to take data and find the best fitting model for a set of data. Here's how we're going to set it up. We have a simple set of data here that we're going to fit a line. We have the point 2, 3, 3, 2, 5, 1, and 6, 0. We're trying to fit a line. Remember, a line can be expressed as mx plus b, where m is the slope and b is the y coordinate of the y-intercept. When you're working with statistics, often they replace the m and the b, and they switch the order. We're going to use beta naught for the y-intercept value and beta sub 1 for the slope, but basically you're just working with a line. And our matrix A, in terms of our normal equations, is going to be the following. I have a column of ones, and then a column that is all of the x coordinates, the 2, the 3, the 5, and the 6. Our y is a vector made of the y coordinates, 3, 2, 1, and 0. Now, why would this be the setup? Well, what we're doing is we're trying to find a linear combination of this data that would equal these y values for a line. So look what we have created here. If we use this matrix A with a column of ones and a column of the x's, and we list our solution matrix as beta naught beta sub 1, when I multiply these two together, I will take 1 times beta naught and add it to 2 times beta 1, and that's forming my line, and I want that to equal the first y coordinate of 3. So when x is 2, I want to get a y of 3. And then for the next row, 1 times beta naught plus 3 times beta sub 1, we want to equal 2. So when x is 3, we want to get a y of 2. And then 1 times beta naught plus 5 times beta sub 1, we want to equal 1. So when x is 5, I want to get a y value of 1. And then 1 times beta naught plus 6 times beta sub 1, we want to equal 0. So 1 times beta naught plus an x value of 6 should give me a y value of 0. So see, with a column of ones here, it's giving you the y-intercept value, and then with the column of the x's next, it's giving me x times whatever the slope is, and then we want to try to get it as close as possible to these y values. So setting up our normal equations, this then is A transpose. Here's A. We're trying to solve for beta naught and beta 1. We want that equal to A transpose times y. Again, that's the normal equations form. And if we go with the method where you're going to type sort of the whole thing into the calculator and do this in all one big step, then if you're solving for beta naught, beta 1, you multiply these together, but then multiply by the inverse of that will give you beta naught, beta 1 by itself. And whatever you do to one side, you do the same thing to the other side. So this side needs to get multiplied by the inverse of this product. And then on that other side was A transpose times y. So if I put all that carefully in my calculator, so notice in matrix A, I have A, and then in matrix B, I have the y's. And so if I then carefully, whoops, we want to clear this, and if I carefully do matrix A, but then we're going to do the transpose. So I go over to math, and program T is the transpose. And then I'm going to multiply by matrix A, and then I want the inverse. So I hit the reciprocal button, and then we're supposed to multiply that by A transpose again. And then we're going to multiply by the vector of y's, which was in B, and we get beta naught of 4.3 and beta sub 1 of negative 0.7. So setting that over here, that means that our best fitting line has a y-intercept of 4.3 and a slope of negative 0.7. So this line best fits this set of data. Now, interestingly, if you have taken a statistics class or maybe a college algebra class, you might have looked at this topic from a statistics point of view, and I have put the data into the graphing calculator, or if you could put the data in Excel also and notice the same thing. And I am going to run the linear regression program, and my x's were in list 1 and my y's are in list 2. And notice I get this information with an R value of 0.98, which is pretty well, negative 0.98. The negative just means that as x goes up, y is going down, but that's a fairly tight value for R, meaning the data fits the line pretty well. And also you could notice that if you go to y equals and you hit vars, and then you go down to statistics and go over to equation, it pieces that together. So notice the linear regression program on the calculator gave me the same thing as my normal equations. Now, you can apply this in more situations than what your statistics class allowed you when you were just learning linear regression. You could have a scenario such as this, where we have radioactive substances A and B, and they have different decay rates of 0.02 and 0.07, and a mixture of these substances at time t contain different amounts of grams of substance A and B. And we are trying to model the total amount Y of the mixture present at a time t. And this is the formula that we're trying to fit. So notice we're not trying to fit just a simple line. We're trying to model Y equal to some constant times e to the negative 0.02x plus some other constant times e to the negative 0.07x. And so my graphing calculator's linear regression problem is not going to help me in this case, but my normal equations will. So what I do is I plug each of the x's into the function part of this equation. So negative 0.02 times 10, negative 0.02 times 11, negative 0.02 times 12, negative 0.02 times 14, negative 0.02 times 15, and then negative 0.07 times 10, negative 0.07 times 11, negative 0.07 times 12, negative 0.07 times 14, and then negative 0.07 times 15. My y then is the set of y's: 21.34, 20.68, 20.05, 18.87, 18.30. And I put this carefully into my calculator as A, and this carefully into my calculator as another matrix. And I actually don't have them in as A. I think I have them in as C and D, but we will take a look here. So if I go down to C, I've got a 5 by 2, and notice there are these messy decimals, but that's because we were raising E to those decimals. But that's A. And then matrix D is a 5 by 1, and it's my set of y coordinates. So carefully, I want to take C, and then I want the transpose of C, and then we're going to multiply by C, and we want the inverse of that product times C transpose, and then multiply by the matrix that has the y values in it. That was D, and I get these coordinates, okay? So those again are the coefficients for my linear combination. So the 19.94 was for the e to the 0.02, negative 0.02, and then the 10.10 is for the e to the negative 0.07. So you can use this idea of best fit and the normal equations to model data to all kinds of different formulas. You're not restricted just to lines or straight polynomials. A very handy discovery.